Thanks very much. And we'll move on now. Max from Code is going to present to us.
Yep, I'm just about to share my screen. This one here.
Oh, and do you want to swap the view? Yeah.
Yeah.
Oh, yeah, there we go.
Oh.
Excellent. That looks good. Thanks.
So yeah, thanks for inviting me for this presentation. You can see on the right-hand side is in this aerial photograph of Queensland. We see the Starra line, the Starra deposits, and second, there's this point option here. We can see that they are perfectly aligned along this ridge, which consists mostly of ironstone, and it's like it's one of the Starra 244 pits, and then further we go to 276, and they are perfectly aligned along this hematite dominated ridge, which has feathered out of the surrounding area. And that's me 2 years ago receiving my first driving lessons in the Queensland outback. Swap slides, yeah. I want to acknowledge my supervisors for the support so far, Jeff, Jonathan, David, and Sean, and GSQ for sponsoring the project, Chinova for sampling assistance and ongoing communication and help, and the Codes Analytical Laboratories and CSL at UTAS for support for the analyzing work. Short outline. First, introduction into pyrite chemistry, why it's important, and a short introduction to the regional and local geology. Then I show you some of the ore zone and pyrite petrography at Starra, and then some of my laser ICP-MS results, short discussion, and some conclusion I come up with so far. It's another view on Starra 444, the open pit. Why pyrite chemistry? Pyrite records chemical information during its growth. You can see here on the right-hand side is a reflected light microscope image of a pyrite grain, which has been etched. It's a relatively cheap and quick method to show that there's some chemical zonation going on. At this stage, we don't know what exactly is going on, but we know that it's a good grain for further analysis. As I said, it's like a relatively cheap and quick method to get an idea that this pyrite grain records some chemical information. And in general, if you look at pyrites from IOCG systems, they are quite distinct from other hydrothermal systems like porphyry systems. But so far, there is no trace element chemistry from Starra pyrites. And then the aims are like to delineate ore forming characteristics of the Starra systems, to define a fingerprint, a chemical fingerprint of the Starra deposit, and potential its application for like a vectoring mineral towards the ore zone. Start with the regional geology. We are up here in the eastern fold belt, the southern part of the eastern fold belt in the Mount Isa inlier. See here, the eastern fold belt in big. We are down here in the southern part at the contact between the Kurridalla formation and the Starfleet formation, and the Starra or deposits are hosted along the Starra shear zone here in black, which consists in this part mostly of ironstones. We zoom in this area and to the local geology. You see here on the western side the Starra shear, and to the eastern side the Selvin shear. Both of them consists of ironstones. The Selvin shear, that's mostly hematite ironstones, and the Starra shear we have magnetite, hematite dominated ironstones. That's what I've tried to show here with the magnetic intensity layer overlaying that there's quite a lot of magnetite in this Starra shear hosted, and that's where we get those Starra deposits. They spread along relative like circa 6 kilometer long interval. 5 deposits from Starra 222 in the south to Starra 276 in the north, and this magnetite K, or the potassic iron alteration footprint, extends for quite a few kilometers beyond the known deposits. we look at the cross section from the Starra 222. I've highlighted here in red. It's the ore body roughly shown in the upper part, associated with those bluish magnetite, hematite, ironstone horizons. And further in the footwall, we get another series of, in this case, magnetite only, magnetite-dominated ironstones that host still some chalcopyrite, but are outside of the modeled ore shell, grade shell, which is the 0.25% copper equivalent grade ore shell. And then even further down at roughly 700-meter depth, we start to see intrusions that are mostly intermediate humorphic composition that also host quite a bit of magnetite and pyrite and chalcopyrite. Those are the samples I'm going to show you, a few from the ore zone, then pyrites from the magnetite-dominated ironstones, and then pyrites from the more albite and chloride alteration facies, and then some pyrite from the intermediate intrusions at the bottom of the drill hole that I sampled. Jump right into the ore zone, somewhere up here. That's the typical Starra mineralogy for the ore zone. We have pyrite here, and this bit brighter yellow, and the darker yellow is chalcopyrite. This iron color is hematite, and then the dark rounded specks are magnetite. There's a laser mount, which I cut out of this section here. It's roughly 1 inch in diameter. And we can again see here the pyrite grains in this bright yellow, and then the darker yellow is chalcopyrite with quite a bit of hematite, and there's still some magnetite left. The ore minerals are mostly chalcopyrite, bornite, and chalcocite, even though in this sample we mostly see chalcopyrite, and the gangue minerals are pyrite, hematite, magnetite, barite, calcite, quartz. Something we see here on this left-hand side picture, that's an XMOD. It's based on SEM images from this laser mount, and shows us the mineralogy relatively well. So we see there's lots of quartz and some chloride in this image. It's another example from the ore zone, pretty much relatively a bit further downhole. In this case, we see lots of chloride. See the green color in this image, which corresponds to chloride. There's some quartz still left as wall rock minerals, but again, a lot of chalcopyrite, a lot of hematite, and some bornite. I'm going to show you like this area in the next slide, a little bit bigger. And you see quite the interesting also mineralogy. So we see that hematite is associated with bornite, and the bornite is replacing the hematite, and then the bornite is also replacing the chalcopyrite in the ore zone, which is and in this right-hand photograph we see this bit golden speck, which is gold. You see down here the image of that corresponds to this red rectangle here. The red arrow points to electrum, silver, gold mineralogy. And what's interesting is we see a lot of gold tellurides, are those bright spots here. So this here is an SEM image again. So we see in the ore zone a lot of sylvanite and calaverite minerals, all like gold, silver tellurides. We now start looking at the pyrite chemistry of those ore zones. It's another example from the ore zone where we did a laser ICP-MS image of pyrite. We see that a couple of elements that are shown here. See that, for example, cobalt has a pretty high variation. It goes from a couple of 100 ppm here in the core to more than 1% in the rim. It's quite substantial. The same with nickel, which is in the core relatively high, but in the rim quite poor. And arsenic is somewhat correlated with nickel. Usually arsenic is often an indicator for decreasing temperature. And in this case, arsenic also correlates with gold and bismuth and tellurium. So, and again, what I saw earlier in the in the previous slide that we have lots of gold tellurides in the system. It's again also shown in the pyrite. So the pyrite also shows that we have inclusions of gold tellurides in the pyrite. And the laser images reveal relatively complex zoning as zonation in the pyrite with dissolution and precipitation structures as well. We now go further down to the magnetite dominated ironstone. It's here an example, relatively black rock. It's all magnetite with some pyrites and some wispy calcite veins cross-cutting the ironstone. That's the circle shows the laser mount. Here is an image, and we see relatively euhedral pyrites overgrown the magnetite. That's again the XMOD image. We see mostly iron oxide, in this case magnetite, some calcite up here with chalcopyrite, and here the pyrite grains. And this pyrite grain I'm going to show on the next slide. It's this one here. I've done another laser ICP-MS image, and we see again very high cobalt concentrations in pyrite. In this case, it's the pyrite core, which has the higher cobalt concentration, more than 1.8% cobalt, and the rim is decreasing, as it like roughly around 1,000 ppm cobalt. Arsenic shows some zonation as well. If the core in this case is higher in arsenic, correlates with cobalt to some degree, whereas the nickel is relatively high in the rim. And again, in the rim of the pyrite, we see gold inclusions, and together with tellurium inclusions. Bismuth is relatively high as well, lots of bismuth inclusions. But again, important is that we see much further down from the ore zone gold telluride inclusions in pyrite. This what we see here with the high cobalt core in pyrite is relatively often described from IOCG systems. It's the more or less the normal IOCG pyrite signature. We go further along the cross section. That's the relatively widespread Albert alteration we see around the Starra system, which is overprinted by potassic iron alteration. In this case, it's the mostly chloride magnetite. And then this chloride magnetite alteration is again cross-cut by calcite veins, which carries some pyrite and chalcopyrite. But we see throughout all three stages pyrite precipitation or formation. We see here, like in this, a couple of pyrite grains in the Albert alteration. So we show you this pyrite grain, this one I've already shown, which has this relatively complex zonation going on. On the right-hand side, we see again the laser ICP-MS image, very low cobalt core. Then it flips to a more than 1% of cobalt in the outer rim. There's probably some dissolution and reprecipitation textures visible as well. They do correlate in this case again with arsenic. And then we see low cobalt, high cobalt, low cobalt, high cobalt rims. This somewhat is similar shows the nickel. In this case, nickel is very high in the core and generally lower in the rim. But again, there's like high nickel, low nickel periods saved in the pyrite growth. And again, so we are like much further down Hohl, below the ironstone lithologies horizons, and we see again gold and telluride inclusions together. So we again see gold tellurides recorded in the pyrite history. And this pyrite grain shows a lot of, as I said, convoluted zonation, dissolution, reprecipitation textures as well throughout its growth history. Then even further down, go into the intermediate geomorphic intrusions. Up here, the photograph from the core is cross-cut by this epidode pyrite calcite vein. It's shown down here in the XMOD. So the green color in this case is epidode, yellow color is pyrite. And the pyrites are relatively euhedral to subhedral, and they overgrow epitode and magnetite. So this is a relatively reduced setting compared to the orso, which was much more oxidized based on the hematite and bornite. And this pyrite again shows inclusions of gold telluride. It's SEM photograph of this section here. And we see those small inclusions with some native gold. We see nickel telluride, which is melanite, and bismuth tellurides in those inclusions, which pop up everywhere in the pyrite grain. If you look at the same grain in a laser ICP-MS image, it's roughly the same area. Again, it's what again, gold tellurides occur quite frequently in the pyrite. Here's nickel shows up as well. So those melanite grains. Cobalt is relatively homogeneously distributed in this pyrite, but again, more than close to 1 weight%, definitely more than 1,000 ppm cobalt. The arsenic is relatively low down here, probably due to the high temperature setting with the intermediate intrusions. And the nickel concentration remains relatively homogeneous as well in the pyrite grain, and is fairly low. Oops, well, wrong direction. So this was a quick overview as through the cross section of Starra vertically. If you now look at the lateral distribution of my sampling process, I sampled roughly 5 locations around Starra, 1 drill hole just south of Starra 222, then 3 Starra deposits, Starra 222, Starra 444, and Starra 276. And then this drill hole quite far, roughly 10 kilometers north of Starra 276, which still intersects magnetite-dominated ironstone, but is quite far away from the nearest known ore deposit or body. And we see again, so shown in this lower plot is all the pyrite images I have made from all those locations, plotted up the gold and tellurium concentrations in those images, and we see that gold mostly occurs in pyrite, which is associated with those 3 ore deposits which I sampled. So 222 has relatively a few high gold inclusions, 244 and 276 as well, whereas the northern drill hole out here and then the one south of Starra 222 is relatively gold poor. So it again shows that pyrite records, at least to some degree, the deposition of gold at Starra. And we also see that all the gold that I find in pyrite, or pretty much most of the gold that I find in pyrite at Starra, is associated with tellurium, while there's some tellurium which is not associated with gold. It's probably something like the melanite I saw, where it's tellurium together with nickel. So to my conclusions, see high cobalt and nickel concentration in pyrite, then it's an indicator for like a high temperature hydrothermal system, generally speaking. So we have like a high temperature later on in this pyrite formation. Higher arsenic concentration usually indicates lower temperature and is to some degree correlated with gold at Starra. And the convoluted zonation we observe in most pyrite grains, it indicates again that we have a relatively complex hydrothermal system with multiple pulses of fluid input, and which was relatively long-lived. That most of the gold that I have found at Starra so far is associated with tellurides. Doesn't matter if we are in the relatively oxidized mineral assemblage associated with the, which occurs in the ore zone, or if we are in the reduced mineral assemblages, it's usually gold together with telluride. Yeah, that's pretty much it. Thank you.
Excellent. Thanks very much, Max. That was great. Now, do we have any questions? Has anybody got a quick question they would like to bring in now, or anyone from the panel?
I was going to ask, oh, there's a couple of questions. I'll save my questions.
Okay.
So we've got a couple from the audience.
Okay, we've got an anonymous one. Are there multiple generations of pyrite? How do you differentiate the effect of host rock?
So yeah, there are definitely multiple generations of pyrite. So I think that, for example, the pyrite in the ore zone is a different generation to the pyrite I find in the further in the intrusions. How do you?
And are you confident? My understanding of the question is, are you confident that there are multiple generations rather than the effect of host rock influencing the pyrite composition? That's my interpretation.
So that okay. So if it's like if it's fluid controlled or if it's from the host rock controlled, the pyrite composition. Well, it's a good question. I think that so we see different, like similar pyrite compositions with different host rocks as well. So I think it's not only host rock controlled. There might be some control of the host rock, but usually it's, I think, mostly reflects the fluid composition that are present.
Okay. One more quick one here from Lucy Chapman, who says, thanks, Max. Is there scope for trialing the eastern hematites in your study? The question of why they are less mineralized or not. Sorry, I think something happened there with the typing.
Yeah, so would be a good question. So they really don't really have that much pyrite in them from what I've seen, and there are not really that many drill holes either. So I sampled one drill hole, which was the very bottom where I found some pyrites. No, I didn't find pyrites, I found other magnetite in them. So yeah, it's the problem that I can't really compare them to the Starra line because they just don't have pyrite in them.
Excellent. Okay, thanks very much, Max. We should keep moving along. There's one quick question there that's just come up. I'll let you answer that online.